Hello, my name is George Clemens, and this video is regarding my final project in ADTA 5560. Submission requirement 1 is to write a report on the dataset that includes, but not limited to, all the critical information on the dataset: the name, data type, website where to get the data, links to download, the time series span, how long the time span is, the data, how many data points, the data structure of the data contained in the data set, and so on. The time series data set that I selected is the minimum daily temperatures data set. It includes the minimum daily temperatures over 10 years from 1981 to 1990 in the city of Melbourne, Australia. The units are in degrees Celsius, and there are 3,650 observations. The source of the data is credited as the Australian Bureau of Meteorology. And it basically includes two fields: the date and the temperature. The field types are the date. The data type of the date field is date, and the data type of the temperature field is float. The date field contains the date the sample was taken, and the temp field contains the temperature in Celsius for that day, the minimum temperature in that day. And as you can see from this first chart, the temperatures are cyclical. It gets warmer in the winter down there and cooler in the summer. Figure 2 shows the average monthly temperature over 10 years. Submission requirement 2 was the design of simple RNN. The assignment was to build, train, and evaluate a simple recurring neural network. It had two layers: the simple RNN and a fully connected layer. The simple RNN layer has 64 neurons. Various modules and libraries, including a time series generator, were loaded. NumPy was used to create a dataset with 2,048 values using the function linspace. The values were between and include 0 and 50. The data was then processed using the sine function. A plot of these values indicates a sine wave. The sine wave data was loaded into a pandas data frame with the x value as an index. The data is split into two sections: 20% for testing, the remainder for training. The data was then normalized into the range 0 and 1. An instance was created to predict the next data set. This is performed using the original data. Then an RNN network was built to utilize the time series data. The number of time series steps is 50. Only one batch is used. The model is used to predict the time series. 50 data points are used to predict the next data point in the series. The same data set is used for both input and output. The consequence of this is that the previous predictions are used in the next prediction. The model was built next. It only includes one feature. The model is defined as sequential. First, a simple RNN layer is added with 28 neurons and a 2D shape. A second layer, called a dense feed-forward neural network, was added. The feed-forward layer has only one output. This is the predicted next value. The graphic on the screen illustrates the neural network described in this section. The model is then compiled with the ADAM optimization algorithm and the mean squared errors cost for the loss function. The model is then fit. The training dataset was trained for 5 epochs. The performance of the model was then visualized. The visualization shows the range of loss. The loss fell quickly after the first epoch. The model was then evaluated. The first batch of data was viewed. This batch consists of the last 50 data points in the training data set. These 50 data points in the training data set are used to predict the first data point in the test data set. The last 49 points of the training data set and the first predicted point in the test data set are used to predict the second point in the data set, and so on. The first batch is converted from 2D to 3D. The batches are 2D. A list is created to store all predictions. A for loop is used to make a prediction for each data point in the test data set. The loop runs 410 times, once for every data point in the data set. The 50 data points are used for each prediction using the prediction method described above. The scaled result is converted back to real-time values using the transform inverse function. The predicted values are inserted into the test data frame as a new column. The matplotlib function is used to both plot the test and predicted data. In this way, the data can be visually compared. The model is similar to the test data. The sine waves shown in this figure have a similar frequency but with different amplitudes. Submission requirement 3 has 3 questions. The first one asks to discuss the cell state of the LSTM cell. The cell state is an information transporting channel. It can transfer information from the earliest part of the sequence to the last. It addresses the short-term memory issues in RNNs and is part of the neural network's memory in addition to hidden memory. An LSTM cell uses gates to regulate the flow of information moving along the path of processing the sequence chain. The second question asks to discuss the concepts of the forget input and output gates of the LSTM cell. The forget gate reviews the values in inputs H-1 and XT to determine what information of the previous cell to keep or forget. The input gate reviews the values from the inputs HT1 and XT to determine what information should be added or saved into the new cell state. The output gate reviews the values from HT1 and XT and the new current cell state CT to make the new current hidden state T at the time set T. The third question is to discuss the similarities between the cell state in LSTM cells and the hidden state in simple RNN cells. The cell state in LSTM cells is much more complicated than the hidden state in simple RNN cells. The cell state provides a LSTM with better long-term memory. Without it, the simple RNN has the tendency to forget information. The cell state performs calculations on information from the hidden state and input data to update the flow of data in the cell state. The simple RNN does not include the cell state and therefore has a long-term memory problem. Both the LSTM and simple RNN cells have a hidden state. Submission requirement number 4 is the design of a neural network, an LSTM neural network. The data used was a subset of the minimum daily temperatures data set. Only 2 years were used, 1981 and 1982. This is a diagram of the network. The LSTM network had 50 cells, and the discard of the dropout layer is 20%. It's the same all the way through. So it consists of an input layer, LSTM layers, dropout layers, and an output layer. The Pandas, NumPy, and Matplotlib libraries were imported. The Keras sequential LSTM, dropout, dense, time series generator, and min-max scalar libraries were also imported. The data was sectioned off into training and testing groups of data. The data was normalized and a time series generator was used. Except for the size of the data used in the training layer, the initial core parameters closely match those used in assignment 4. The size of the training layer data was 10%, but was changed to 15%. The sequence of the LSTM was 60 and the number of neurons is 50. The percentage of data discarded by the dropout layers is 20%. The length of the time series sequence is 60 and the batch size for training is 30. The model included one feature and was defined as sequential. The first LSTM layer has 50 cells. The activation layer is ReLU. The next layer is a dropout layer with 20% discard rate. The second LSTM layer has 50 cells. The second dropout layer also has a 20% discard rate. The third LSTM layer also has 50 cells and uses ReLU activation. And the model was compiled using the ADAM optimizer and MSE loss. The model was then trained and visualized. You can see that the loss drops quickly, similar to other RNN-C or LSTM models. And then here you can see the test data right here. The full input data set was pre-processed and the time series generated was created for forecasting. The LSTM model was then built, compiled, and fit. The data was inverse transformed back into true values. New temperature data was imported for the time period from 1/1/83 to 4/7/83. A prediction was created, visualized, and compared to existing data. The chart below, figure 9, shows the prediction trend overlaid onto actual data for that time period. Submission requirement 5 is where it gets a little more interesting. We get to design a neural network. And I found a paper titled Recurrent Neural Network Regularization, in which they not only propose increasing the dropout rate to 65%. By the way, the maximum dropout rate allowable in Keras is 50%, but also drastically increases the number of cells in an LSTM layer. So I put together a new design that starts with the first LSTM network with 1,000 cells. The third one has 500 cells, and the second one has 500 cells, and the third one has 100 cells. The first discard layer uses a 50% discard rate, and the second one uses a 25% discard rate. So this is a list of the updated core parameters. The percentage of data used for testing remained at 15%. 3 layers of LSTM were used. The first layer had 1,000 neurons, the second 500, and the third 100. 2 dropout layers were used. The first dropout layer had a discard percentage of 50%. The second one had a discard rate of 25%. And the length of the time series input is 60. The batch size for training is 32, and the number of epochs for training is 100. And then had to build, train, test, retrain, and forecast the model. It included one feature and was designed as sequential. As earlier stated, the LSTM cells in the LSTM layers was increased drastically. The activation function is ReLU, and so the model was, again, the ADAM optimizer with the MSE for the loss function. The result was actually disappointing. Here we see the forecast with the first model, and then one we just did. It's actually flatter than the previous model. So increasing the dropout rate and the cells in the LSTM layer actually give us a worse prediction than the first first model. And so, although it was not required, I still was very curious as to whether or not I could see any prediction of the cyclical nature of the data. And so, what I did was to take the last model and increase the data to the original data size, all 10 years, and also to increase the size of the forecasted data, actually sequential data used, to 2 years also. So here's a result of that. Over here you can see a little bit of an uptick on the forecast, which we didn't see before. It was a little bit flat. So maybe that's an indication that that more data would help. Maybe if there were 100 years of data, it would have made a difference. But then again, it would have taken probably several days of processing just to get that result. Submission requirement number 6 required the comparing of the performance of 2 networks, but I had 3. The first, or what I considered to be the baseline network, consisted of the following parameters. The training layer data was 15%. There were 3 LSTM layers, and the number of neurons is 50. The percentage of data discarded by the dropout layers is 20%, and the length of time, the time series sequence is 60, and the batch size for training is 30. For the second network, the percentage of data for testing remained at 15%. The same 3 layers of LSTM were used. The first LSTM layer was increased to 1,000 neurons. The second was to 500, and the third LSTM layer was increased to 100 neurons. 2 dropout layers were used. The percentage of discard with the first dropout layer was increased to 50%. The percentage of drop with the second dropout layer, or I should say discard, was increased to 25%. The length of the time series sequence was kept at 60. The batch size for training was kept at 30. Well, I guess was increased to 32. And the number of epochs for training was kept at 100. Despite the changes made, the results were similar. The temperatures vary with season, and the data was very cyclical. However, the predictions did not reflect any type of cycle. For this reason, I decided to create a third network. This network included the full 10 years of data as compared to the first 2 networks that only included 2 years of data. The time series input was increased to 730, or 2 years. The percentage of training was increased to 20%, which was 2 years of data. The parameters on the LSTM layers and dropout layers remained the same as in Network 2. These changes did not have any appreciable effect on the results. No cycle was indicated in the prediction. Submission requirement number 7 is a project report. So this final project covers all the topics that have been covered in the course. This project primarily includes information on how to build various neural networks. However, the building of neural networks is predicated on the ability to create a Keras server in the Google Cloud platform and connect to it. A connection to the Keras server requires the use of 2 Google Cloud SDK shells and 2 SSH instances. They're used to form a connection and to redirect browser information over an SSH connection to a Jupyter notebook. Python and Keras libraries are used within the Jupyter notebook to develop and execute neural networks. Part 2 of the project required the generation of a sine wave dataset and the creation and testing of a simple RNN neural network. The dataset included 2,048 values and was created with the function linspace. The values were between 0 and 50 and included 0 and 50. The data was plotted and indicated a sine wave. The simple RNN used this data to predict the time series. 50 data points were used to predict the next point in the series. The model was sequential. The first layer was a simple RNN with 128 neurons. A second layer, called a dense feed-forward layer, was added. The model was compiled with the ADAM optimization algorithm with mean squared errors cost for loss function. Part 3 of the project required the discussion of the cell state of the LSTM cell. The cell state refers to information from the earliest part of the sequence, or transfers information from the earliest part of the sequence to the last, and addresses the short-term memory issues in RNNs. In addition to hidden memory, it is a part of the neural network's memory. An LSTM cell uses gates to regulate the flow of information moving along the path of processing the sequence chain. Also required was the discussion of gates in the LSTM cell. The gates can be considered neurons by themselves. They assist the cell with either forgetting the data if necessary or processing the data. Another requirement of Part 3 was the discussion of the similarities between the differences. Similarities and the differences between the cell state and LSTM cells and the hidden state in simple RNN cells. The primary difference is the existence of the cell state in LSTM cells. Part 4 of the project required the building of an LSTM neural network. The data used was a subset of the minimum daily temperatures dataset. Only the years 1981 and 1982 were used. Below is a diagram of the LSTM network. The network consists of an input layer, LSTM layers, dropout layers, and an output layer. The Pandas, NumPy, and Matplotlib libraries were imported. The Keras sequential LSTM, dropout dense, time series generator, and min-max scalar libraries were also imported. The data was sectioned off into training and testing groups of data. The data was normalized and a time series generator was used. Part 5 of the project required a redesign of the neural network built in Part 4. The network built in Part 4 is considered, I considered a baseline network. The network built in Part 5 was an attempt to improve the performance of the network built in Part 4. Parameters were changed to that effect, the most prominent of them being the increase in the number of nodes in the LSTM layers and the increase in the dropout rate. The discard rate in the dropout layers. None of the changes significantly improved the result. Therefore, a third network was built. This network utilized a full 10 years of data instead of the 2 years in previous models. The sequence of data used in the input was increased to 365 days, and the date range for the prediction was increased to 2 years. This also resulted in no significant improvement in the prediction. The changes made in the third network were done in an attempt to reveal a cyclical pattern in the prediction. This did not happen. What was learned from the models was a simple RNN does not have a very good memory. Also, although the LSTM performed better than the RNN, its predictions were very general and would not reveal a cyclical pattern in the data. Both the simple RNN and the LSTM only use one feature, and that is by design because they use sequential data. It was also clear that increasing the complexity of an LSTM does not necessarily increase the accuracy of the predictions. My conclusion is that LSTMs can be used to make general predictions on sequential data. What I was hoping to learn was to somehow use multiple features in a neural network and to make predictions that reveal cyclical patterns in data. The ability to make more accurate predictions and to reveal cyclical patterns in predictions would be very valuable. These types of models are probably already used within Wall Street institutions to manage stock trades. It is very likely that these types of predictions are very complex and utilize proprietary algorithms. Additional research may reveal methods used to make more accurate predictions of sequential data. A couple of more items of note. I found the method of connecting to the Google Cloud platform to be somewhat more difficult than I think that it should be, although I've actually completed some Google Cloud Platform courses and really can't think of any easier way to do it. However, opening two Google Cloud SDK sessions and two SSH sessions and a browser to access Keras sounds like typical Google thing to do, but it seems like there should be an easier way. But one of the things I did do is, I don't know if you can see it here, but I used the SSH connection available via the GCP Google Cloud Platform to upload files rather than to use the Google shell on the computer. You can actually go here and upload and download files. I did use it to download files also, especially if I had crashed the server, actually messed up the connection. At one time, I attempted to increase the processor speed, number of processors actually, but doing that changed the whole connection on the system, and so I would have had to recreate it, which I didn't want to do 2 days before my project was due. So I set it back, but in the interim, I was able to download my Jupyter files. And so one more item of note. Since I did have 10 years of data to work with, on my last model, perhaps I could have created a fourth model. I could have increased the training data to 50%, since I had so much data, to see if it would reveal any cycle in the data. I did start to see a slight curve up, so maybe with some additional work, a cycle would have been revealed. I'm just very curious about that. That's why I created the third network. Thank you for watching my video. This concludes my presentation. Thank you.